right, so we've looked at angle measure and radian measure in section 4.1, and hopefully we've got a good handle on that. What we're now going to take a look at is something called the unit circle and some trig functions or trigonometric functions, and we'll just kind of introduce this with a starter question. We're going to graph this right here. We've actually graphed something similar to this before in this class, but let's take a good look at this and kind of investigate it using some of the tools that we talked about. So one thing that we can do to graph any type of function is make an XY table, but sometimes that can be a little bit tedious. So we want to be smart about this and kind of reduce the amount of work that we have to do. So one thing that we'd want to do is we'd want to figure out maybe if there's any symmetry. So let's check to see if it's symmetric with the y-axis. If it's symmetric with the y-axis, you'll remember we can plug in a negative x and we get the exact same thing. So if I plug in a negative x and I square that, and then I've got the y squared and the 1, I get plain old x squared, y squared equals 1. So this is symmetric with the y-axis. So there's a yes right there. So we know that the left side is going to look the same as the right side. If we check symmetry with the x-axis, we actually plug in a negative y for y. So we're going to do x squared and then plus, plug in a negative y, square that. Well, if I do that, I get x squared plus y squared equals 1. So I get the same thing. So the answer there is also a yes. It's also symmetric with the x-axis. So now let's find the intercepts. Usually the intercepts are a good thing to find and graph. So let's plug in a 0 for x. If we do that, we get 0 plus y squared equals 1. If I then solve that by taking the square root, I get plus or minus 1 for the y coordinate. And then let's do the same thing and let's find the x-intercept. So let's plug in a 0 for y. So that's going to be x squared plus 0 squared equals 1. So that's going to give us x squared equals 1, which means x is going to equal plus or minus 1. So here's what we get if we were to sketch those 4 points. And this is good because it shows that it is symmetric with both of the axes. So here are the 2 points. This is 1, 0. This is negative 1, 0. And then this would be 0, 1. And this point down here would be 0, negative 1. And you'll notice that this is kind of an interesting function. You can't plug in numbers that are bigger than 1 because automatically if you square it, that would make the answer bigger than 1 because you're just going to be adding the two of these things together. So we can't plug in x's that are bigger than 1 or less than negative 1, and same thing for y. So we're going to get answers kind of in this little region right here. We could also take this and we could solve this for y. If we did that, I'd move the x squared to the other side. So I'd get 1 minus x squared. And then we could try and get y by itself by taking a square root, and we'd get 1 minus x squared. Of course, we'd have to have the plus or the minus there. So what we end up with here is we end up with a circle that's centered right on the origin, whose radius is 1. And just to double check, let's say I pick this point right here. So here's an x value. Let's say that's 1/2, and then I come up and I find this point right here. So I'm interested in finding the y coordinate when x is 1/2. Well, to my eye, it looks like it would be just a little bit less than 1, but let's double check and see. So let's plug in a 1/2 in right here. So if I do that, I get 1/2 squared, and I'm going to zoom in here so we've got little extra room to work, plus y squared equals 1. Well, this would be 1/4 plus y squared equals 1. So if I move that to the other side, that would be y squared equals 1 minus 1/4. So that would be y squared equals 3/4. So if I took the square root, I'd get plus or minus radical 3 over 2. And if you type that into your calculator, let's just check and see what that is. So that's going to be square root 3 divided by 2. So we get about 0.87. So I'm going to write radical 3 over 2. So we've got 0.5 comma 0.87. And that looks pretty good right here. And you'll also notice that when we did that, we ended up with another point down here that would have had a coordinate of 1/2 comma negative radical 3 over 2. Okay, so we've got that symmetry going on, and gosh, we've probably got a point over here and a point over there. So what we get here is a circle that's centered at the origin whose radius is 1. So we kind of want to keep that in mind because this particular graph is going to come in handy a little bit later on. Now, let's review a couple of things from your geometry class. You probably learned about something called special right triangles. Special right triangles are 45, 45, 90s and 30, 60, 90s, and we normally don't put the degrees on here, but I suppose we could. So that's what we call these, 30, 60, 90s and 45, 45, 90s. And I'm going to show you a couple of examples, and these are things that come up a lot. Well worth your time to memorize because you'll probably see these on the ACT or something like that. So good things to memorize. So let's talk about how we get a 45, 45, 90 first. So this is what we're going to do here. I'm going to make a square, and that square, I'm going to make the sides 4 units long. Each one of these is 4 units long. And then what we're going to do is we're going to come along here and we're going to cut that right in half. We're going to go draw a diagonal right here. So that's going to cut this in half. Now remember, this is a square, so this angle right here is a right angle. So is that one. All 4 of these are right angles. And if I draw a diagonal on a square, it bisects or it cuts this angle in half. So if this angle used to be 90 degrees, what I've done is I've cut it in half, so this is 45 degrees right here. And you'll remember that the 3 angles in a triangle have to add up to be 180 degrees. So if this is 90, these two need to add up to be 90. So this one's also 45 degrees for another reason other than the fact that we cut this right angle right here in half. So here's what we're dealing with. This triangle is a 45, 45, 90. So I'm just drawing a copy of this. And this is 4, and this is 4. And here's the question. I don't know what this is. Now I'm going to use a choice of variables here. I'm going to call that one C for a good reason. And you'll remember that if we've got a right triangle, a squared plus b squared equals c squared. This is the Pythagorean theorem. So I'm going to plug in, I'm going to call this side a and this side b. So this is going to be 4 squared plus 4 squared equals c squared. That's going to be 16 plus 16 equals c squared. That's going to be 32 equals c squared. So if I were to take the square root, I'd have radical 32 for c, which if I simplify that, this is 5 2, so I've got, well, I'll write it this way. This is 4 times 4 times 2. So there's a pair of 2's that I can take out. So that would make c equal to 4 radical 2, okay? So I'm going to replace this, and this is going to be 4 radical 2. And you can do that with any 45, 45, 90. You can think of it as a square. You can say that these two sides, will, since it came from a square, those are going to be the same. And run through this process, and you'll get something like that that we're going to talk about down here. So no matter what these sides are, these are always going to be the same. So if you know one leg on a 45, 45, 90, you know the other leg on a 45, 45, 90. Now, how do we go from a leg to the hypotenuse? Well, you'll notice that this has a radical 2 on it. So whatever this is, whatever this leg is, you times it by radical 2 to get to this side right here. So we're going to times by radical 2. And if you've got the hypotenuse and you're trying to find the leg, if you're going the other direction, well, if you times by radical 2 to go to in this direction, you're going to divide by radical 2 to go in this direction. So 45, 45, 90s are relatively simple, and they're really nice. So let's take a look at what we get if we've got a 30, 60, 90. So let's start off with this, and I'm going to change colors here. So we're going to start off with what we call an equilateral triangle. Now you'll remember an equilateral triangle, all the sides and all the angles are equal. So every one of these angles is equal. And if they add up to 180 degrees, that means each one of these is 60 degrees. So all of those are 60-degree angles. Okay. Now I don't have any 30-degree angles, you'll notice. So here's what we're going to do. We're going to drop a line straight down here. Okay. Now it's going to cut this angle right in half, and it's going to cut that side right in half. We call it an angle bisector and a segment bisector. I'm also going to go through here and remember equilateral, the sides are all the same length. So this is 4, and this whole thing right here is 4. Well, what I'm interested in now is I'm interested in just this triangle right here, from here to here to here. So I'm going to draw that one over here. And because I dropped that line straight down here, that's a 90-degree angle, and this one's 60. Well, if you think about it, this one's got no other choice but to be 30 degrees. So there's our special right triangle, our 30, 60, 90. And let's put some measurements to this. This side right here appears right here, the whole thing, so that's going to be 4. This one drops straight down here and cut this side in half, so this is going to be 2 units right here. And then we've got to find this one over here. Well, I'm going to make a convenient choice here. I'm going to call that one A. So you'll remember that if I square the legs and add those together, that's going to be the hypotenuse squared. That's what the Pythagorean theorem says. So I'm going to have a squared plus, this is going to be the other leg, so this is going to be 2 squared, equals c squared, so this is going to be 4 squared. So I get a squared plus 4 equals 16, so I get a squared equals 12, and then I take the square root and I get a equals, well, if I take the square root of both sides, this is going to be a 2 times a 2 times a 3, so this is going to be 2 radical 3. And I don't have to worry about the plus or the minus on there because this is the side length on a triangle. It certainly couldn't be negative. So I'm going to go ahead and erase this, and this is going to be 2 radical 3. Okay? So notice what we've got here. These sides all started out to be the same, and this one got cut in half. So this short leg, notice it's across from the smallest angle, this short leg right here is half of the hypotenuse. And then the long leg here, you'll notice that there's a 2 here, but it's been multiplied by radical 3. So let's take a look at our diagram right here. So this would be a generalized 30, 60, 90. Here's the hypotenuse and here's the short leg. Now you do need to remember that everything on a 30, 60, 90 goes through the short leg. If you've got the short leg, it's easy to figure out the rest of it. So to go from the short leg to the hypotenuse, we're going to times by 2. We're just going to double it, just like right here. 2 times 2 would be 4. If we're going the other way, if we wanted to know how to go from the hypotenuse to a leg, we're going to divide by 2. Now, to go from the short leg to the long leg, we're going to times by radical 3 going this direction when we go from the short leg to the long leg, and it should make sense that if we're going from the long leg to the short leg, we're going to divide by radical 3. Okay? So that's a little bit about 30 special right triangles, 30, 60, 90s, 45, 45, 90s. I'm going to shrink this down again, and let's take a look at a couple of special cases here. So these are generalized cases. These two sides would both be x, they're the same, and then we take whatever that side is, multiply it by radical 2 to get the hypotenuse. Everything goes through the short leg, that's why I've labeled this one as x. So to go from the short leg to the hypotenuse, we times by 2. To go from the hypotenuse to the short leg, we divide by 2. And to go from the short leg to the long leg, times by radical 3. And to go from the long leg to the short leg, we divide by radical 3. Well, let's say I gave you a special instance. And we're going to use these measurements quite often, and these are going to come up a whole bunch. Hopefully you're already aware of this stuff right here. These are some things that I want you to memorize, and you'll see these over and over and over again, so it would really be a good idea if you got these memorized. So let's take a good look here. This is a 45, 45, 90, and I've got the hypotenuse, and I want to know what the short leg is, or sorry, what one of the legs is. So to go from the hypotenuse to a leg, I divide by radical 2. So if I take 1 and I divide it by radical 2, I normally don't leave it like that. I'd normally rationalize the denominator. So let's see what we get here. I get a radical 2 on the top and a 2 on the bottom. So this is going to be, radical 2 over 2 for this one right here. And the cool part about a 45, 45, 90 is once I've got one leg, I've got the other one. So this is going to be radical 2 over 2. So I've got the two legs there and all three sides. And again, you're going to see these measurements come up quite often. And then here's a 30, 60, 90. I've got the hypotenuse. Again, the easiest thing to do is find the short leg. To go from the hypotenuse to the short leg, we're going to divide by 2 right here. So this is going to be a 1/2, and it would be much better if you kept these as fractions, so please do that. And then to go from the short leg to the long leg, I simply times by radical 3. Well, if I do 1/2 times radical 3, that's going to be radical 3 over 2. So again, hopefully these are ideas that you're already familiar with. This right here, if you haven't memorized these side lengths right here, you're definitely going to want to memorize those because again, they're going to come up over and over and over again as we go through and do these next couple of sections. So this book introduces trigonometry in a couple of different ways, and we're going to start by looking at trigonometry with respect to the, whoops, I spelled this wrong. Let's just erase that right there, with respect to the unit circle. So let's talk about what the unit circle is. Unit circle is pretty easy. It's almost self-explanatory in the name. The unit circle is a circle that's centered at the origin, so we put it in a nice convenient location, with a radius of exactly 1 unit. So we go 1 unit in each direction. So that problem that we did in the graph that we came up with in the starter question, that is the unit circle. So what we're going to do here is we're going to go through and mark this, and I know we've done this a couple of times, but we're going to go through and mark the quadrantal angles. That might be a new term for you. We're going to mark the endpoints of each one of these quadrants in degrees and radians. Okay, so we're going to mark this as, this would be 0 degrees, 0 radians. This is going to be 90 degrees, and that's going to be the same as pi halves radians. This is 180 degrees, and that's the same as pi radians. Remember, this is going to be 270 degrees. That's the same as 3 pi halves radians. And then if we go all the way around the circle, that's 360 degrees, which is the same as 2 pi radians. So remember, the advantage radians have is they're real numbers. They're not anything made up. We're just talking about how big the arc is with respect to one radius. Remember, a radian literally means one radius as an arc length there. And they make things down the road a heck of a lot easier. We're also going to, just as a reminder, so we keep these straight, we're going to mark each one of these in as their decimal equivalent. So this is going to be 0. Pi halves is 1.57 approximately. Pi, of course, is 3.14. 3 pi halves is 4.71, and if we go all the way around the circle, that's 2 pi, or 6.28. So if we had an angle of like 2 or something like that, 2 would put us about right here, somewhere in quadrant 2. If we had an angle of 5, this is 1.5, there's 3, there's 4.7. 5 would be somewhere around here in quadrant 4, okay? So now that we've got that, we're going to do something that we really need to be very, very well familiar with by the time we're done with this. I've got a big picture of a unit circle here, so if you'll follow along and do what I do. Each point on the unit circle has both an x and a y coordinate. And we're going to move around the circle in a counterclockwise direction, so in a positive angle measurement direction. And we're going to do that in increments of pi fourths. And before we do that, I'm going to go through and I'm going to mark this in radians. So this is going to be 0. This is going to be pi halves. This is going to be pi. 3 pi halves, and again, all the way around the circle would be 2 pi. We're going to go through and mark it off in pi fourths. So this is going to be pi fourths. So that's a fourth of the top half of the circle. So I'm going to mark right here. So that's pi fourths. Okay, so there would be 1/4 of pi, 2/4 would be pi halves, 3/4 is going to be right here. So this is going to be 3 pi fourths. And let's see. Tell you what, I'm going to put these angle measurements inside here. So this is going to be, whoops, pi fourths. This is going to be 3 pi fourths. And this is going to be, well, let's see, 1 pi fourth, 2 pi fourths, 3 pi fourths, 4 pi fourths, 4 pi fourths. Those would cancel, so that's just going to be pi. This is going to be 5 pi fourths, 6 pi fourths, which would cancel, will be this. This is going to be 7 pi fourths, and then all the way around the circle would be 8 pi fourths, or that would be 2 pi. So we're all set to go there. We've marked that. If it's more helpful for the time being, again, you've got to get used to radian measurement here. But if you want to think of this in terms of degrees, we're talking 45 degrees. So we're going to take this and we're going to mark each one of these points. So there's a point on the unit circle. Here's a point. Here's a point. Here's a point. We're going to mark each one of these points as an XY pair. So this XY pair right here, I went over to the right. Remember, this is the unit circle. So 1 unit to the right, I didn't go up or down. So that's going to be 1, 0. Then, well, let's do this one right here. This point right here, I didn't go right or left. I just went up 1 unit. So that would be 0, 1. If I were to come over here, I went back 1 unit, but didn't go up or down. So you'll notice it's kind of symmetric right there. And then I've got this point right here where let me make some space right here. Hopefully you've got more space than I do. So this is going to be 3 pi halves. I didn't go right or left, but I just went down one. So again, we've got some symmetry there. Now let's talk about this point right here. It does have an XY coordinate. This radius right here would be 1 unit. And this angle measures pi-fourths, or it measures 45 degrees. So if I were to drop a line straight down here, I've got a right triangle, and again, this would represent the radius, so that would be 1 unit. So if you'll remember, we actually did this problem just a second ago. It's right here. If the hypotenuse, or the radius in this case, is 1, that means the horizontal leg is radical 2 over 2, and the vertical leg is radical 2 over 2. So that means I know the x-coordinate. I would have gone over radical 2 over 2 and up radical 2 over 2, the exact same amount in each of those directions. So I've got that taken care of. Well, if I were to do the same thing over here, like swing this triangle over here, again, this is 1 unit, that would make this, we're going in the negative direction, so that's going to make this coordinate negative radical 2 over 2. But I still went up, so that's going to be radical 2 over 2. Okay? I'm going to take that and do the same thing down here, and hopefully we've got the hang of this now. So this would be negative radical 2 over 2, and we went down also, so they both would be negative radical 2 over 2. And then I've got this other one over here, last one that I need to do with, as far as this part of the problem goes. So I went to the right radical 2. It's symmetric with this one right here. They have the same x-coordinates, so that's going to be radical 2 over 2. But instead of going up radical 2 over 2, I went down, so that's going to be negative radical 2 over 2. So that's what I've got right there. Okay, so we've gone through and we've marked each one of these points in 45-degree increments, or in pi-fourths radians, and we've got all 8 of those points around the unit circle. Well, what if we wanted to do this in increments of pi-6, or in other words, 30 degrees? Well, let's run through and see what happens. Let's draw where that would be. If this is 45 degrees, 30 degrees would be about right here. So I'm going to write that as pi-6. Again, 1/6 of the top half of the circle. If I did 2 pi-6, that's going to put me about right here. But 2 pi-6, we think of that as pi-thirds. So I'm going to mark that as pi-thirds. And then if I did, so I've got 1 pi-6, 2 pi-6, 3 pi-6, 3 pi-6, cancel those, that's the same as pi-halves. Okay. Then I've got one over here, kind of symmetric there, and then I've got one over here, and then the same thing's going to happen on this bottom part of the circle. Okay. We're going to have one, make that look a little bit better. Looks like that. Now, what we want to do is we want to go through and we want to figure out what each one of these is as far as radian measure, and we want to write it down as far as what the coordinates on the unit circle are. So let's see, 1 pi-6, 2 pi-6, 3 pi-6. This would be 4 pi-6, 4 pi-6. Cancel that off. That's going to be 2 pi-thirds. So we've got 2 pi-thirds. Let's see, 5 pi-6. That doesn't reduce at all. 6 pi-6, that's going to reduce. 7 pi-6. 8 pi-6. 8 pi-6. Let's see, that's going to be 4 pi-thirds. Oops, let me write that inside. 4 pi-thirds. Let's see, we're at 9 pi-6, 10 pi-6. So that's going to be 5 pi-thirds. And let's see, another one, that would have been 11 pi-6, and that's not going to reduce. So you'll notice another way that you could think of this is you could count in thirds. 1 pi-thirds, 2 pi-thirds, 3 pi-thirds, 4 pi-thirds right here, 5 pi-thirds right there, and then 6 pi-thirds would be all the way around the circle. So let's go ahead and find out what these coordinates are right here. Now, if I draw this triangle, and let me get rid of a bunch of this other stuff here so we don't have that cluttering things up. I'm going to draw this right triangle right here, and I want you to think for just a second about the measurements on that triangle. We know what the hypotenuse is, just like on that last part of the problem, we knew what the hypotenuse was. And now we want to figure out what the legs are. What's this leg right here, and what's this leg right here? Well, if this is pi 6, this is 30 degrees. And I know the hypotenuse. Well, this is the short leg over here, and remember, it's pretty easy to figure that part out because all you do is take the hypotenuse, divide it by 2. So this one right here is going to be 1/2, and then to go from the short leg to the long leg, remember this is the 60-degree angle, so it would make the longer of the two legs. This is going to be times by radical 3, so that's going to be radical 3 over 2. So that means the coordinates on the unit circle would be, I would have gone to the right, my x-coordinate would be radical 3 over 2, y-coordinate would be positive 1/2. So let me get rid of that right there, and then we'll do this one more time right here, and then hopefully we can speed this up just a little bit. Think about how big this angle is. It's pi thirds. Hopefully we know what that is in degrees really quickly. That's 60 degrees. So that is this little picture right here. So that means that this short leg is 1/2, and this would be radical 3 over 2. So that means the coordinates on the unit circle for this point would be, I would have gone to the right 1/2, and then it would have gone up radical 3 over 2. Now, that hopefully looks a little bit familiar because it's actually the problem that we did in the starter question where we confirmed that point right there, 1/2 comma radical 3 over 2, about 0.5 comma 0.87, and hopefully that looks about right. Now, rather than go through and draw every one of those triangles again, because there's a lot of them at this point, let's use our heads and think about this. These 2 points are symmetric. So they're just as far above the x-axis for both of them, but we went to the right on this one, we went to the left on this one. So this one's going to be negative 1/2 radical 3 over 2. Now I'm going to skip ahead just a little bit. Follow this one straight down. Remember we talked about the symmetry here? Okay. This means we would have gone the same distance to the left, so that means our x-coordinate is going to be negative 1/2. But instead of going up radical 3 over 2, we went down radical 3 over 2. And then I can take this one and swing it over here. So instead of going to the left 1/2 and coming down, I'm going to go to the right 1/2 and come down. So that's going to be positive 1/2 negative radical 3 over 2. And I want to just double check and confirm it this way. Take a look at this one right here and this one right here. They are symmetric with the x-axis. That means the only thing that should change is the y-coordinate. So you'll notice the y-coordinate here is positive and the y-coordinate here is negative, but they have the same x-coordinate. Okay, so we're in good shape there. Let's go ahead and finish this off then. Let's swing this one straight over here. You'll notice that the angles would be the same here. The difference would be instead of going to the right radical 3, I went to the left radical 3. So this is negative radical 3 over 2 comma 1/2. Swing that one down here, back negative radical 3 and down 1/2. So that's negative radical 3 over 2 comma negative 1/2. And then let's see, gosh, we've got all of these done except for this one right here. And on this one right here, I can swing this one over on this side, making that positive, or take this one and swing it down here, making the y-coordinate negative. So this is going to be radical 3 over 2 comma negative 1/2. And you'll notice a couple of things. All the coordinates are positive in quadrant 1. That's what we'd expect. All the coordinates in positive or in quadrant 2 have a negative x-coordinate because we went back and then we went up. So each one has a positive y-coordinate. Both are negative in quadrant 3, and then in quadrant 4 they've got a positive x-coordinate because we went to the right, and they've got a negative y-coordinate because we went down. Okay. So this is something I'll actually hand out a nice handout where you've got this, looking nice and all that sort of stuff. But for the time being, I just want you to use this. Make sure that's accurate. If you need to take a second look at that, if you need to watch the video again. Again, we're interested in having all of these angles in radians. They're pretty easy to understand when they're in degrees. And we also want all of these coordinates on the unit circle. And this is something that you need to memorize. There's no getting around it. I know it looks kind of ugly, but nonetheless, that's what you've got to have memorized. It'll really come in handy down the road. Okay, if you'll go ahead and flip the page over, now we're ready to start talking about trig functions. And we're not going to be able to finish our entire discussion today, but we're going to be able to get the basics out of the way. So what we want to realize is because those coordinates on that unit circle occur in such a systematic fashion. I mean, look at the way these start at 0 and get bigger, and then they get smaller. We're talking about the y-coordinates here. And the same numbers appear over and over and over again. And because of that, we want to give a name to this special type of relationship. So we're going to call these trigonometric functions, trigonometric functions. All right, and there are three main trig functions: sine, cosine, and tangent. And we say sine, cosine, and tangent, that's how they're spelled. We do abbreviate them like this. Please don't say sin, cos, and tan. We actually say sine, cosine, and tangent. And here's a definition that this textbook uses, or at least one that we're going to start off with. And we're going to say, let t be the central angle on a circle of radius r. So we're talking about a circle centered at the origin. Okay, I'm going to make a picture like this, where we've got a radius here, and then we've got this x and y coordinate right there. So if we've got a situation like that, then the point on that circle corresponding to, oops, this should be a t right here, sorry for that. The point on the circle corresponding to that angle right here, so here's this angle t, is going to be the y coordinate over the radius, or y over r. The cosine of t, the cosine of that angle, is going to be the x coordinate over r, and the tangent is going to be the y coordinate over the x coordinate. And these are by definition, and there are reasons they came up with these. And you may have heard of sine, cosine, and tangent and had it explained another way. We're going to get to that, but this is the way we're going to approach this in this book for right now. So this is something you're going to want to keep track of. But for the time being in this section, because we're talking about the unit circle, and the radius on the unit circle is 1, we can state the following. Well, that would make these r's equal to 1, so that means the sine of the angle is just the y coordinate. The cosine of the angle is just the x coordinate, and because an r doesn't appear in there, that's still going to be y over x. Now, each one of these trig functions has what we call a reciprocal trig function, and their names are cosecant, secant, and cotangent. Okay? So, because they're reciprocals, reciprocal, remember, means you take a fraction and you flip it over. So the reciprocal is going to be 1 over y. So we just take this and we literally just do the reciprocal of it. So 1 over y here. Secant would be 1 over the x coordinate, and the cotangent of an angle on the unit circle is going to be the x coordinate over the y coordinate. Okay, now I've got a question for you. Do we need to be careful with any of these trig functions? So let's take a good look at each one of these. Well, each one of these, even in this definition right here, they all involve some sort of ratio, some sort of fraction. We need to be careful not to divide by 0. Okay, we're going to have a domain issue. We're going to have a problem figuring out an answer if any one of these ends up being divided by 0. So let's go ahead and take a look at example number 1, and we're actually going to go through and we're going to compute some trig values now. So it says evaluate the trig functions for each value of t. So I've got a different value of t, a different angle that we're going to use for each one of these, and then a couple of different choices for the trig functions that we're going to use. So remember, I'll have this to where we can see this. So the sine is the y coordinate, the cosine is the x coordinate, tangent would be the y coordinate over the x coordinate, cosecant is 1 over whatever the y coordinate is, secant is 1 over whatever the x coordinate is, and cotangent is the x coordinate over the y coordinate. So let's think about what this looks like right here. So if I have an angle of pi 6, so again, we're thinking on the unit circle, so it looks like this. Here's pi 6 right here. So this is going to be pi 6, which is also equal to, or actually I'm going to do this. I'm just going to say we've got pi 6 right here, which is also 30 degrees. So I've got this 30-degree angle right here. Well, let's think about how long this was. This is the short leg, so that was 1/2, and this is radical 3 over 2. So that means that coordinate is radical 3 over 2, comma 1/2. Well, literally, the sine is just the y coordinate, so that's just going to be 1/2. The cosine is just the x coordinate, so that's going to be radical 3 over 2. Got that one taken care of. And the tangent is going to be the y coordinate, which is 1/2, over the x coordinate, which is radical 3 over 2. Now we need to take this mess and clean it up just a little bit. So I'm going to flip this one over and multiply. So this is going to be 2 over radical 3. I'm going to cancel those so I get 1 over radical 3. Now if you wrote this answer, it wouldn't be the end of the world. But normally we do rationalize the denominator. So here's what we're going to do. I'm going to multiply by radical 3 over radical 3. So that's going to give me as an answer radical 3 on the top and 3 on the bottom. So the sine of pi 6 is 1/2. The cosine of pi 6 is radical 3 over 2. Okay, and then I'll write this one down here. Save some space here. The tangent, the tangent of pi 6 is equal to radical 3 over 3. Okay, all right. So let's do this next one. So our angle is 5 pi fourths. So let's think about where that is and what that would look like. So 5 pi fourths. There's 1 pi fourths, 2 pi fourths, 3 pi fourths, 4 pi fourths. 5 pi fourths would be here. On the unit circle, if you want to flip back a page, we've got this point pretty well figured out. If that's 1 unit, and this is that would be corresponding to a 45-degree angle right here. This is going to be radical 2 over 2, and this is going to be radical 2 over 2. But we do need to be a little bit careful, and this is a very common mistake, so please pay attention to this. We went back, so that needs to be negative, and we went down, so that needs to be negative. So we be really careful. Make sure that that point, and notice if we come back up here and we take a look, there for 5 pi fourths, there's the x-coordinate of negative radical 2 over 2 and the y-coordinate of negative radical 2 over 2. So now we need the cosecant. The cosecant is going to be 1 over the y-coordinate, so that's negative radical 2 over 2. So I've got 1 divided by a fraction, so I'm going to take that and I'm going to flip it over and I'm going to multiply. So this is going to be negative 2 over radical 2, which again, I normally rationalize the denominator, so I'll make that just a little bit bigger. Radical 2 over radical 2. So here's what we end up with. We end up with negative 2 radical 2 over 2, so I can cancel this, so I end up with negative radical 2. So the cosecant of 5 pi fourths is negative radical 2. Okay, so there's my answer on that one. If I were to take a look at the secant is 1 over the x-coordinate, so that's going to be 1 over negative radical 2 over 2. Well, I'm going to go through the same process. They both started out as 1 over negative radical 2 over 2, so that means that the secant of 5 pi fourths is going to be negative radical 2 also. Okay, now let's take a look at the tangent. The tangent is the y-coordinate, which is negative radical 2 over 2, over the x-coordinate, negative radical 2 over 2. Same thing over same thing, and they're even the same sign, so this is going to be a 1. So that means the tangent of 5 pi fourths is a 1. Okay? So I've computed several different trig values right now for each one of these particular angles that we plugged in. And now let's take a look at this next one, because this gets a little bit interesting. Okay, on this one right here, think about where 3 pi halves is. Pi halves, 2 pi halves, 3 pi halves were right here. Think about what the coordinates would be. We don't go right or left, so the x-coordinate is 0 and the y-coordinate is negative 1. So the cosine is going to be 1, or excuse me, just whatever the x-coordinate is. So that's going to be 0. So that means that the cosine of 3 pi halves, cosine of that particular angle is 0. So we've got our answer there. And then the secant is going to be 1 over the x-coordinate. So we're dealing with this one right here. So that's going to be 1 over 0, which is undefined. Okay? So the secant of 3 pi halves is undefined. And let's take a look at this last one, the cotangent. Cotangent is going to be, let's see, that's going to be the x-coordinate over the y-coordinate. So that's going to be 0 over negative 1, so that ends up being 0. So the cotangent of 3 pi halves, 3 pi halves is 0. Okay, so I've computed a bunch of different trig ratios there, which is good. And let's take a look at a few more. Now, For those of you that this is new, again, you may need to pull this up and look at this video again and kind of think about how these things are related and why these are the correct answers. We're now going to take a look at a couple of other aspects of trig functions, and we're going to finish up this discussion tomorrow. So let's take a look at what happens if we go around the circle in a counterclockwise direction. So there's nothing that would stop us from doing that. Oh, sorry, we've done it in a counterclockwise direction. We're going to take a look at what happens in a clockwise direction, so a negative angle, or what would happen if we went around more than once. So we're going to compute the sine of this angle, the cosine of this angle, and the tangent for that angle. Same thing for these other two. So let's take a good look at this. If I were to draw a picture for this, it would look like this. This is a 30-degree angle right here. And this is 1 unit again, because we're on the unit circle, remember. Well, this would be radical 3 over 2, and this would be, we went down, so that would be negative 1/2. So that means the sine of negative pi 6 would be the y-coordinate. That's going to be negative 1/2. Now I want the cosine of negative pi 6. Well, that's going to be the x-coordinate, radical 3 over 2. So I've got that one taken care of. And now I want the tangent of pi 6. Tangent of pi 6 is going to be the y-coordinate over the x-coordinate. So that's negative 1/2 over radical 3 over 2. Again, I'm going to flip that one over. So that's going to be 2 over radical 3. So I've got negative 1 over radical 3, which if you'll remember, we rationalize that and we're going to have negative radical 3 over 3. So that means the tangent of negative pi 6 is negative radical 3 over 3. So I've got my 3 answers there. Now let's take a look at this next one. For this next one, we're going to go around the circle. Let's see, 5 pi. There's 1 pi, 2 pi, 3 pi, 4 pi, and 5 pi. So we're going to end up right here. So again, what we did is there's pi, 2 pi, 3 pi, 4 pi is twice all the way around the circle. We end up right here, okay? So we're, again, on the unit circle, think about where we'd be. We're right here. This would be negative 1, 0. So again, I want the sine of 5 pi, I want the cosine of 5 pi, and I want the tangent of 5 pi. So sine of 5 pi would be the y-coordinate. That's going to be 0. Cosine of 5 pi is going to be the x-coordinate. That's going to be negative 1. And the tangent of 5 pi is going to be the y-coordinate over the x-coordinate. Well, let's see, y-coordinate over the x-coordinate, that's 0 over negative 1, so we end up with a 0 right there. Okay, so that's each one of those. All right, so let's take a look at this one right here, and we'll see how far we get in the next couple of minutes. So negative direction, so we're going to go in a clockwise direction. 5 pi halves. So there's 1 pi halves, 2 pi halves, 3 pi halves, 4 pi halves, and 5 pi halves. So here is, again, started here, all the way around to there. Okay, so that would be an angle of 5 pi halves, or negative 5 pi halves, excuse me. And on the unit circle, we just didn't go right or left. We went straight down 1 unit, so this would be 0, negative 1. So I want the sine of negative 5 pi halves, cosine of negative 5 pi halves, and the tangent of negative 5 pi halves. So we want each one of those. We're plugging in each one of these angles into those trig functions, and then we want to see what the answer is. Well, the answer for the sine, again, is the y-coordinate, so that's negative 1. The answer for the cosine is the x-coordinate, so that's 0. And the answer for the tangent is the y-coordinate over the x-coordinate, so that's going to be undefined. So I've got each one of those 3 trig ratios for those particular angles. Some that went around more than once, some that went in a clockwise direction, some that went in a negative or in a counterclockwise direction. Okay, last thing I want to do now is I want you to, we'll compute these and then we'll think about this. So this is just the sine value. This is all we want. So think about where 0 radians would be. So I want the sine of 0 radians. So that would be, we haven't opened up this circle at all. It just is this point right here on the unit circle. So that's 1, 0. So that's going to be the y coordinate. That's going to be 0. So we've got the answer right there. 2 pi. 2 pi would be 1 full revolution. So we go all the way around the circle. So we're right back here to start with. Again, 1, 0. And I want the sine of 2 pi. So it's just the y coordinate again. So that's going to be 0. And then 4 pi. So let's see, in a counterclockwise direction, positive direction, around once, around again, and I arrive at this point again, which is 1, 0, and I want the sine of 4 pi. So the sine of 4 pi, again, whatever the angle is that we're plugging into the trig function, in this case, it's going to be 4 pi into the sine function. That's going to be the y coordinate, so that's going to end up just being 0. So the question here is, do you notice anything about each one of the answers? Well, that's pretty simple. They're all the same. But the question is, why are they the same? Why are they the same? Why is the sine of 0, 0? Why is the sine of 2 pi 0? And why is the sine of 4 pi 0? Well, if you think about what happened here, we didn't go anywhere on that one right there. We ended up at this point here, 1, 0. Went all the way around the circle and ended up here again. All the way around the circle and ended up there again. We're going to be in exactly the same place on the unit circle because they're coterminal. Okay, they're all coterminal. They have different measurements, but they end up in the same place. Because of that, we end up with something called a cyclical function or a periodic function. And you can think of a period as the time it takes to repeat a cycle. So in this case, the y coordinates start off at 0. They get big, they get all the way up to 1, they shrink back down to 0, then they go negative, and then they hit 0 again, and then they just continue doing that over and over and over again. We got the same answer on this one because all we did is we went from 0, got up to 1, back to 0, down to -1 for a y coordinate, and then back to 0. We're right in the same place, and this is going to happen every single time. So how much does it take to go around the circle so that we can repeat? Well, in this case, for sine and cosine, it takes 2 pi units, 2 pi radians in order to do that. Okay? So that's enough to get started. When we pick this up tomorrow, we're going to talk about the domain and the range. We're going to talk about some other interesting things, but we'll finish up this page, and then you'll have enough that you can get started on the assignment. If you wanted to do anything, you could do some of the very easy problems on the assignment, or really I'd recommend if there's anything in this video that didn't make sense, I'd go back and I'd take a look at it again.